Dear students, in your previous class we discussed about different types of aromatic electrophilic substitution reactions like halogenation, nitration and sulfonation reactions. Today we will be discussing about some more aromatic electrophilic substitution reactions, that is about Friedel reactions. So today we are going to discuss about two important Friedel reactions, that is about Friedel alkylation and Friedel acylation reaction. So what are Friedel reactions? Two scientists, Charles Friedel and James Krafts, they introduced two important electrophilic substitution reactions of arenes for the preparation of alkyl arenes and acyl arenes. So electrophilic substitution reactions of arenes for the preparation of alkyl arenes and acyl arenes are known as Friedel alkylation and Friedel acylation. That means electrophilic substitution reaction, if an electrophilic substitution reaction involves introduction of an alkyl group, that is R group, that is known as Friedel alkylation, and if an electrophilic substitution reaction involves introduction of an acyl group, RCO group, that is known as Friedel acylation. So let us see one by one. First let us discuss about Friedel alkylation. So what is Friedel alkylation reaction? Benzene reacts with an alkyl halide in the presence of anhydrous aluminum chloride to yield the corresponding alkyl benzene. That is Friedel alkylation reaction. Other Lewis acids like BF3 and FeCl3 may be used instead of AlCl3 in Friedel alkylation, but reactivity is lower in such cases. So in Friedel reaction what happens is that benzene reacts with alkyl halide RX in the presence of Lewis acid. Here we are using aluminum chloride. We can use BF3 and FeCl3 instead of AlCl3, but the reactivity will be slow in the case of if we use BF3 and FeCl3, but when we use AlCl3 the reactivity will be very high. That's why we are using AlCl3 in common alkylation reactions. So when we treat benzene with alkyl halide, the R group from the alkyl halide will get substituted on the benzene ring. By replacing the hydrogen atom from the benzene ring, the R group will get substituted. So we will get an alkyl substituted benzene. For example, benzene on reaction with methyl chloride, in the presence of anhydrous aluminum chloride, toluene, we will get toluene as the final product. That means CH3 group will get substituted on the benzene ring by replacing hydrogen atom. So if you are asking how can you produce toluene from benzene by using Friedel alkylation, what you have to do, you have to treat benzene with methyl chloride in the presence of anhydrous aluminum chloride in order to produce toluene. Similarly, you can produce ethyl benzene by treating benzene with ethyl chloride. So you have to change the alkyl chain, alkyl group, in order to produce different types of alkyl benzene. If we use ethyl chloride, we will get ethyl benzene. If we use methyl chloride, we will get methyl benzene. Then hydrogen from benzene reacts with chlorine from from ethyl chloride, and HCl will get removed and the ethyl group will get attached on the benzene ring and produces ethyl benzene. Then another reaction, benzene on reaction with isopropyl chloride. You had to write the structure of isopropyl chloride. You had to write and practice the structure of isopropyl chloride. It is a secondary alkyl chloride. So when benzene on reaction with isopropyl chloride in the presence of an aluminum hydrous chloride, in the presence of anhydrous aluminum chloride, we will get isopropyl benzene. Isopropyl group will get attached on the benzene ring by replacing the hydrogen atom. So product is isopropyl benzene, or it is also known as cumene. So how can you produce cumene from benzene? So you have to treat benzene with, for that you have to treat the benzene with isopropyl chloride. So the product will be cumene. Now let us discuss about the mechanism of Friedel-Crafts alkylation. So it involves mainly 3 steps. First step is the generation of the electrophile. Second step is the formation of the arenaceous ion. Third step is loss of a proton from the sigma complex. So first step is generation of the electrophile. That involves the alkyl halide reaction with anhydrous AlCl3 to yield a carbocation which acts as the electrophile. So in Friedel-Crafts alkylation, electrophile is a carbocation R+. So alkyl halide on reaction with anhydrous aluminum chloride, we will get alkyl cation and the base AlCl4 minus. This base will react in the last step, third step. A carbocation will rearrange to a more stable carbocation if such rearrangement is possible. So if there is a possibility for the formed carbocation in the first step to rearrange into a more stable carbocation, that carbocation will rearrange to a more stable carbocation. If this happens, the major product in a Friedel-Crafts alkylation reaction will be that with the rearranged alkyl group on the benzene ring. So if there is a possibility for a carbocation to rearrange into a more stable carbocation, then the more stable carbocation will get attached on the benzene ring, and the final product will be different from the original alkyl group. Then the second step is the formation of the arenaceous ion or carbocation or sigma complex. The carbocation R+, that is electrophile, attacks benzene to form another carbocation arenaceous ion called sigma complex, which is stabilized by resonance. This is the rate determining step of the process. So second step involves the formation of a carbocation, also known as arenaceous ion or sigma complex. In this step, the formed carbocation from the first step attacks on the benzene ring. That involves a slow step and forms a carbocation. When the electron pair shifts to this carbon will get a positive charge and this carbon becomes negatively charged. So onto the negatively charged carbon, this carbocation will attack and the charges will get neutralized. So a carbocation will produced. Carbocation means a positively charged species with positive charge on the carbon. So this carbocation is resonance stabilized. The positive charge is dispersing throughout the ring. Then the third step is the loss of a proton from the sigma complex, that is the carbocation. Then AlCl4 minus present in the reaction mixture abstracts a proton from the carbocation and restores aromaticity to the ring to yield the alkyl benzene. So AlCl4 minus, that is formed in the first step of the reaction, abstracts a proton from the carbocation. This is the structure of carbocation. Resonance hybrid structure is shown here. So AlCl4 minus abstracts a proton from the carbocation. This AlCl4 minus will act as a base and will abstract a proton from the carbocation and produces alkyl benzene by restoring the aromaticity to the ring. That means this AlCl4 minus abstracts a proton, means H plus ion will take up by this AlCl4 minus and producing HCl and AlCl3. Then the electron pair of this bond will shift to this CC bond and producing and restoring the aromaticity of the ring, and the final product will be alkyl substituted benzene. This is the mechanism for Friedel-Crafts alkylation. Here the electrophile is carbocation, alkyl cation. So let us know more about Friedel-Crafts alkylation. The mechanism for any Friedel-Crafts alkylation reaction can be written using same steps by replacing R in all steps with the actual alkyl group being introduced, provided there is no rearrangement of the initial carbocation produced to a more stable one. So if you are asked to write the mechanism for methylation reaction, that means reaction between benzene and methyl chloride, you have to replace the alkyl group R group with CH3 group. Then you can write the mechanism of the Friedel-Crafts alkylation reaction. Thus, to write the mechanisms for the reaction of benzene with methyl chloride, ethyl chloride and isopropyl chloride, replace the R groups with CH3, replace the R group with CH3, CH3, CH2, then isopropyl group respectively. The products will be toluene, ethyl benzene and isopropyl benzene respectively. So we can replace the R group with methyl group, ethyl group and isopropyl group in order to produce toluene, ethyl benzene and isopropyl benzene. However, if the carbocation R plus initially produced rearranges to a more stable one, R dash plus, then R has to be replaced with the R dash from step 2 onwards to obtain C6H5 R dash as the major product. Then C6H5 R will be a minor product in such cases. So if there is a chance for a carbocation to rearrange to a more stable one, then you have to introduce the alkyl group, the more stabilized carbocation. You have to introduce the more stabilized carbocation in your mechanism. Then the more stabilized carbocation substituted product will be the major one, and the other one will be the less stabilized carbocation will be the minor product. Less stabilized carbocation substituted product will be the minor one. When benzene is treated with N-propyl chloride in the presence of anhydrous aluminum chloride, the major product is isopropyl benzene, because the N-propyl cation produced rearranges to the more stable isopropyl cation. Here is an example for the rearrangement rearrangement of a carbocation to a more stable carbocation and the final substitution product. Here we have N-propyl chloride, which on treating with anhydrous aluminum chloride, the base will be AlCl4- and the carbocation will produced. That is the primary carbocation and propyl cation CH3CH2 CH2+. There are two possibilities. This carbocation can react with the benzene and can form the normal propyl benzene. This is the minor product, because there is a chance for this carbocation to rearrange to a more stable carbocation. This is primary carbocation which can rearrange to a more stable secondary carbocation, that is isopropyl carbocation. Here there occurs 1,2 hydride shift. 1,2 hydride shift means from the second carbon. This is the carbocation carbon, positively charged carbon. On the adjacent carbon there are two hydrogen atoms. From this carbon, one of the hydrogens will move by taking the electron pairs and shift to this carbon. So the hydrogen will move from this carbon as H-, then that will shift to this carbon. So the positive charge will get neutralized by the negative charge of H-. So this carbon will become CH3 and this carbon will become CH+. So this is a secondary cation, carbocation, that is isopropyl cation. Then which on reaction with benzene ring producing major product, that is isopropyl benzene. It is also known as cumene. So here there is a possibility for the carbocation propyl cation to rearrange to more stable isopropyl cation. So the more stabilized carbocation substituted product will be the major one, and the less stable carbocation substituted product will be the minor one. This is one additional information about Friedel-Crafts alkylation. There is the possibility, if there is a possibility for the carbocation to rearrange to a more stabilized carbocation, then that type of product will be the major one. So this is an example for that type of reaction. Let us continue with another type of Friedel-Crafts reaction, that is Friedel-Crafts acylation reaction. In this reaction, benzene reacts with an acyl halide or acid anhydride in the presence of anhydrous aluminum chloride to yield the corresponding acyl benzene, or it is also known as anaryl ketone. So in this reaction, benzene reacts with acyl chloride. This RCO group is known as acyl group, which on reaction on treating with, that means acyl chloride on treating with benzene in the presence of aluminum chloride and anhydrous aluminum chloride, this RCO group will get substituted on the benzene ring by replacing the hydrogen atom. That hydrogen atom will react with chlorine of this acyl chloride producing HCl. So acyl group, RCO group will get attached on the benzene ring producing acyl benzene. So if you are asked to convert a benzene into a ketone, this is a ketone, aromatic ketone, you had to treat benzene with acyl chloride in the presence of anhydrous aluminum chloride. Now let us see the mechanism of Friedel-Crafts acylation reaction. So it involves three steps. First step is the generation of the electrophile, second step is the formation of the rhenium ion, and third step is the loss of a proton from the sigma complex. So first step involves generation of the electrophile. In Friedel-Crafts acylation, the electrophile is RCO plus acylium ion. So acyl chloride or acid anhydride reacts with anhydrous aluminum chloride to yield acylium ion RCO plus, which acts as a electrophile. So in Friedel-Crafts acylation, the reaction is with the reaction occurs between anhydrous aluminum chloride and acyl chloride. Then in this reaction, what happens is that the Cl atom will get removed from acyl chloride as Cl minus and will attack on AlCl3. So from acyl chloride, Cl atom will get removed as Cl minus and will attack on AlCl3 and forming AlCl4 minus. And this RCO plus ion will be the remaining part, RCO plus. That means the acylium ion will form from this acyl chloride when Cl minus will get removed from this acyl chloride. So this acylium ion RCO plus, that undergoes resonance stabilization. This electron pair will shift to this bond. So this oxygen will get a positive charge and this positive charge will get neutralized. So there is a resonance stabilization possible for acylium ion. Then so first step is the formation of the, in all cases first step is the formation of electrophile. In halogenation, nitration, sulfonation, then alkylation, acylation, all the reactions, in all the aromatic electrophile substitution reactions, the mechanism involves the formation of electrophile in the first step. The second step involves the formation of the rhenium ion. There is a carbocation or sigma complex. The carbocation RCO plus, that is the electrophile, attacks benzene to form a carbocation, a rhenium ion called sigma complex, which is stabilized by resonance. This is the rate determining step of the process. This is a slow step So it is the rate determining step, whereas the first step is the fast step. So in the second step, the electrophile attacks on the benzene ring. RCO plus is the electrophile which attacks on the benzene ring and produces a sigma complex or carbocation or arenine ion. That means when electrophile attacks on the benzene ring, this electron pair will shift to this carbon. So this carbon will get a positive charge, this carbon will get a negative charge. On to the negatively charged carbon, this acylium ion will get attacked. So this charge will get neutralized. So this carbon will have a positive charge. Then this charge will get dispersed throughout the ring and forming resonance stabilizer sigma complex. This is the resonance hybrid structure for the acylium ion. So these are the two steps for the Friedel-Crafts acylation. Let us discuss about the third step. This is the third step and last step of the acylation reaction. So in this step, loss of proton from the sigma complex occurs. That means AlCl4 minus present in the reaction mix. That means it is formed in the first step of the reaction that abstracts a proton from the carbocation and restores aromaticity to the ring to yield acyl benzene. So in the second step, there is a loss of aromaticity. The benzene ring loses aromaticity in the second step. So in the third step, that lost aromaticity restores by the abstraction of proton by the base AlCl4 minus. So when this base abstracts a proton from the ring, it will release the electron pair. This HC carbon electron pair will leave here. That electron pair will shift to this bond and therefore the aromatic ring will restore its aromaticity and producing acyl benzene. That means an acyl group will get attached on the benzene ring. An acyl group will get electrophilically substituted on the benzene ring in the acylation reaction. So these are the two electrophilic substitution reactions, that is Friedel-Crafts reactions. One is Friedel-Crafts alkylation reaction, another one is Friedel-Crafts acylation reaction. In Friedel-Crafts alkylation reaction, the carbocation or the electrophile is carbocation. In Friedel-Crafts acylation reaction, the electrophile is acylium ion RCO+. These are all about aromatic electrophilic substitution reactions. Some common aromatic electrophilic substitution reactions. Thank you.